welcome to this webinar of Ontotext. Today we're going to talk about how to review hidden relationships in data and risk analytics with our CEO, Atanas Kyriakov. Today's webinar is going to be recorded, so please, if you feel impatient or your link breaks down, don't worry, you'll receive a link of this webinar at the end, as well as all the questions that you ask during this webinar. For any question that you may have, I do advise you to use the Q&A panel, which you can find in the top right corner of your screen. Please restrain yourself from using the chat box, which is also available, but we prefer if you use the Q&A panel. Today's webinar is going to be around 1 hour, so sit tight and enjoy it. And we're going to start. So now I'm going to give the word to Atanas Kyriakov, who's going to start his presentation.
Hello. This presentation is all about an experiment with linked data and user analytics and combining the two. And it's not a sort of a very robust platform yet. That's part of our internal experiments and research of Ontotext. Of course, that it's built on top of a ton of existing products, but the concrete integration exercise of getting these data sets, combining them with news and doing something is something that started a couple of months ago. The total effort that got into this is less than 1 person a month. So it was rather an exercise for ourselves to see how easy are these technology to be applied for these kind of tasks, and how far you can get within a few days or few weeks of work rather than a few person years. So I sort of started presenting this platform on the previous webinar that I had end of March. The platform is called FactForge News. So then I focused on what we do with DBpedia geonames and to some extent with news. And now we extend it with also further data sets and mapping to FIBO and further experiments and like relationship discovery and pattern recognition that we didn't have before. So I'll start off with the brief description of the use case, then I'll describe how we designed and how we made the sandbox, what data sets got in, how we mapped it to the FIBO ontology, and so on and so forth. And then I'll talk about the real stuff, the concrete queries and examples and things that we can do with this data. To start with, the ultimate goal would be to allow to detect this kind of scenario. So imagine you have a big company called Bucks Café that's located in Seattle that controls a company called My Local Café through another company in the Cayman Islands. Imagine My Local Café is going to a bank and asking for a loan, and they're trying to research them a little bit. And they present themselves as a small local business, while in fact they are not local business at all. They're controlled by one of the big guys, and it may well be that this big guy is currently in some sort of financial troubles. This would be a very big game changer for the decision how to score the loan application of My Local Café. So what it takes to implement these kind of things. So as you see, for this purpose, you have to combine what you have in gray here, the information about companies, like which company controls which other company and so on, where they're located, geographic information, so that you know that Seattle and New York City are part of the United States, while West Bay is part of the Cayman Islands. And so on and so forth, and you need to load this data in a database that can help you do some find out, discover some extra links. Right, all these links that you see with dashed yellow arrows, these are things that the engine was able to infer based on extra semantic information provided in the ontology, schema of this database. The trivial example being in OWL, that is the language used for RDF-based graph databases. You can say that the relationships are transitive. In the example with the controls relationship here, this means that if there is a chain of such relationships, the first guy in the chain controls all the others. In this case, that big Bucks Café controls My Local Café. That's an isolated example. It doesn't look very fancy when you look at one such relationship. But if you can combine this at a big scale across multiple data sets, and you get millions of these relationships, and then they start combining with one another, it makes a lot of difference. So yeah, that's essentially the use case, and that's what we are aiming for. And now I'll give you an idea how you can move in this direction. To start with, for those of you who are not that familiar with what are open link data, that's a web of data. These are some of the central data sets that were out there back in 2007. And for instance, the DBpedia is just a structured version of Wikipedia. You have essentially all the most of the factual information out of Wikipedia represented in graphs and loaded in the database. You have geonames. We also use geonames here. That's a geographic, very well maintained, very regular database with information about all locations, geographic features on Earth. And then you have dictionaries and many other things. So this web of data was growing ever since 2006-07. In 2011, it wasn't possible to paint it on a readable diagram, and it keeps growing, and now there are thousands of different data sets that you can use for the purposes of, like those that I'm just demonstrating with two of the central data sets. So we have loaded in FactForge News the English portion of DBpedia, or the English version of DBpedia. That's about 500,000 statements, 500,000 relationships, links in this knowledge graph. Then we have geonames. The entire geonames is about 150 million statements. Also links, the same as relationships between these two data sets, which essentially, GraphDB, our triple store database engine, has optimized support for our CMS, and this essentially allows you, when you have mappings between the identifiers used for one and the same entity into different data sets, this allows you to use them interchangeably. So we can use the identifiers from DBpedia and the query and touch information that's in geonames, and vice versa, across the entire data set. So anyway, we have about 500,000 mappings like this. So 500,000 of all the locations that are in geonames are mapped to something that's in DBpedia. On top of this, we have loaded information from company registries. There is an initiative called Global Legal Entity Identifier. I will speak more about this later on. That's not too big, 3 million statements. And we also loaded in this mix metadata about news, 130 million statements. The total size of the repository is about 1 billion triples statements, 2/3 of which are explicit, and there are about 300 million inferred statements. Like these yellow dashed arrows, they were inferred 300 million of them. Because a bare-bone graph database, be it a triple store engine or something else, isn't good in things like geographic constraints and full text search and many other things. We have several plugins for GraphDB that are used in this sandbox. One of them is RDF that allows you to provide you something like PageRank for each node in the knowledge graph, in RDF graph. There is a geospatial plugin that allows you to efficiently do constraints like nearby or distance, these kind of things. full text search, and so on and so forth. So a few words about the global legal entity identifier data. We took this data from a place called Global Market Entities Identifier Utility. We took a dump. Then we archivized it. It's about 3 million explicit statements, about 211,000 organizations. The coverage of this one isn't too big. I mean, for instance, in DBpedia, there are about 500,000 organizations. And in Dun & Bradstreet and other commercial data sets, you can find millions of organizations covered. Sorry, hundreds of millions. Still, these 300 million statements, these 200,000 organizations, are already a body of data that's worth playing with, and we started playing with it. One of the interesting relationships that's in there is relationship that points out which entity is the ultimate parent of the control hierarchy of which other entity. So there are about 10,000 relationships of this type, and the ultimate parents altogether are about 1,600. We also, well, to provide some sort of meaningful experience, we had to map these archivized GLEI data with the rest of the data sets. So far we mapped about 3,000 organizations, to be precise, 2,800 organizations from GLEI to DBpedia, and yeah, it took us about a day to implement these mappings. So yeah, it would take us another day or two to map probably another like few tens of thousands of these data of these organizations with reasonable quality. And then the rest of them, there will be some that will never appear in DBpedia because they are not popular enough. Because the criteria by which the entities are selected to be included in this GLEI data dump are completely different from whether something appears or doesn't appear in Wikipedia. You can see here a sample of this data set. Like this is the record, a part of the record for ABN AMRO, a Dutch bank. So there is plenty of information of like what is the business registry where this company is registered, what is the local number, and yeah, actually the most important part of this whole thing is that I forgot to mention, GLEI is actually a big initiative about transparency. So after the financial crisis in 2008, people got started different initiatives for a better sharing of information and all sorts of things that will make the financial affairs one step more transparent, so that we have a better chance of spotting and avoiding this kind of financial troubles. So that's an initiative to essentially combine company registry information across all countries on Earth, and to give each and every legal entity globally unique identifier, so that information across different countries can be more easily interrelated and analyzed. So that's a really big initiative that, I mean, most of the big organizations related to financial regulations and the big banks and so on are part of this initiative. And this dump is, to an extent, I mean, one of the first results. But it's getting mass, and probably in 1 or 2 or 3 years we can expect most of the developed countries to have officially started publishing this kind of global legal entity identifier information about the companies that are registered in their legislation. So this will be growing, and this 3 million is just the start of the thing. But yeah, the whole thing is that each entity is given a 20 symbol number. So you have all this information about headquarters, city and state, as well as where the entity is registered, because it could be different from the headquarters, and so on and so forth. This is the number. So GLEI, legal entity identifier, is that is BFX. This is the identifier of ABN AMRO in this system. You can also demonstrate. You can also have records that say that for whatever reasons, for ABN AMRO, for the same legal entity, there are two records, two identifiers that are duplicates. That's useful for data cleaning. This data is fairly currently not. I mean, the coverage is not uniform, so you can see that in terms of countries, about half of these records are from the United States, and then, but there are also other countries which come with non-trivial numbers. About the ultimate parent relationships, you see that the distribution is again sort of strange, and out of 10,000 links altogether, almost 2,000 are related to Goldman Sachs. So yeah, there is space for improvement and getting more information of this type in the future. So that's what it is, and we can keep moving. So a few words now about the news metadata. So I'd rather make a quick demonstration. We have a service called News on the Web now, where we essentially demonstrate how our dynamic semantic publishing platform, and how you can essentially recognize concepts, entities, all sorts of things in the text, and link them to by tagging them with their identifiers to concrete objects and concepts in a big knowledge graph. And in this case, we analyze all the news with respect to big knowledge graph that contains Wikidata, DBpedia, and a few other things. So that's handy. You see that we recognize all sorts of locations, organizations. We have relevance, confidence for each and every organization. We also can recognize quotes. That's not that hard. Relationships between organizations, they can overlap, like Jim Braid, Chief Investment Officer, whatever. So you see, it can get fairly complicated, but that's all the information that you need anyway. Then you can jump over from reading the news article to say, well, actually, what's Halliburton? That's a big company. Get some information about it in the box on the right-hand side. That's part of the information that we have in a knowledge graph. Get trends of popularity, so how often this company was mentioned. Get related other related news to Halliburton. And get information about like what other entities most often occur together with Halliburton in the news. Baker Hughes, I have no idea who Baker Hughes is, but I can click on it, get news that are about both Halliburton and Baker Hughes. and keep exploring. So that's an experience that allows you to basically jump from the text to the knowledge graph and back and navigate and explore in a more natural way than just reading one news article after another. But that's all background. So the important thing is that we essentially through the purpose of the experiment with PyTorch News, we're getting metadata from now and loading all this information about like what entities are mentioned in which news articles, and also the relationships. We are loading them together with the other data that I'm talking about. So we have about 10,000 news a month. It's a constant feed, so we keep getting information all the time. And it generates fairly rich metadata. Like on average, we have about 70 tags per news article. Good. What's the distribution? Yeah, they come in different categories, and for analytics purposes, for instance, for all sorts of ranking and data science that you may want to do, we find it very useful to deal with one category at a time, because trying to derive some meaningful patterns that work well for both sports and business isn't that trivial. At least that's our experience. Another thing that you can see is that we recognize key phrases, but beyond that, the entities that we have in the knowledge graph, all these organizations, locations, people, accidentally it appears that we have about the same number of mentions for each of these three categories, for organizations, locations, and people. And you also see down there towards the bottom of this table that we have relation person row. So these are all these relationships that we managed to extract, relationships between a person and the row of this person within an organization that we managed to extract from the news, and we have about 250,000 of those. There are also relationships between companies and so on and so forth. That's part of the one goal of this experiment is to use also this extracted relationship for analytics purposes. When you get that much information in, it's getting not that easy to navigate. So I'll show you what kind of tools we use internally and what's built in GraphDB. So that's the workbench. You can go to data and start class hierarchy, and you see this lovely diagram. So it's essentially showing all the classes. And you can see that DBO agent, this is agent class from DBP deontology is the biggest one. It's actually a super class for person and organization. If you don't like to see all these name prefixes all the time, you can switch them off. And well, on the right-hand side, we see that we have like almost 3 million instances of this class, 3 million agents, about 2.5 million people, and as I said before, about 500,000 instances of organization with all the subclasses, like 60,000, 65,000 companies, of which like banks and airlines are the biggest, and so on and so forth. We can also from here jump over to explore a concrete entity of this type, just a sample, so that you can get better feelings about it. And the domain range graphs with like entity relationships, but I wouldn't go into this because that's not the main goal of this presentation. What I wanted to show you here is that we are dealing with, on the left-hand side, there is scale, and we currently in this repository have 1,100 different classes. You can, if you prefer to have a less busy diagram, we can say, well, which are the 20 most popular. Here here you have them. But 1100 classes is quite a lot, so you need these kind of tools to be able to do something meaningful and to find your way around it. Now let's talk a little bit about FIBO. FIBO is the Financial Industry Business Ontology. That's again part of these transparency initiatives. It's mostly supported by the financial regulators, and all the big banks are part of this game. Also, so it's an ontology, a schema that allows these big financial organizations to represent data about all sorts of things in a unified schema, so that regulators, for instance, can more easily combine information that comes from different banks for analytical purposes. So it is an upper level ontology that starts all the way from very basic things like people, organizations, agents, and these kind of things, and goes up to very specific things for the financial industry, like a different type of contracts that the banks have and the conditions on whatever security contracts, for instance, and this kind of stuff. So they start from the most basic thing, and in this respect, it is an upper level ontology that defines concepts about most of the stuff that we care about. But it also has a very, very specific stuff about financial relationships, deals, contracts, and their parameters. So we took this ontology and we loaded it. The ontology comes in R, that's the schema language of the semantic web, and this type of RDF-based graph databases. And we loaded it in the repository. It took several seconds. In GrabDB, you can choose what type of, how complex inference and based on what rules to be used. In this case, we basically made it with R2RL. That's probably the most popular profile of the R specification. Altogether, these are about 5,000 statements. And after inference, we inferred another 15,000, and these, altogether 20,000 got stored in the repository. You can see that, in FIBO we have about 300 classes just in these two modules that we loaded now, the Foundations module and the Business Entities module. You can. This is the domain range. The domain range diagram. It shows what type of what relationships can point to people, and what relationships can originate from a node that represents a person, like physical location and these kind of things. So now let's talk a little bit how we did the mapping. So we tried to make a minimalistic mapping, and we mapped only what we needed. In this case, it was mapping organization, company, and person from the DBPD ontology into the corresponding classes in the FIBO ontology, formal organization, corporation, and person. We also mapped the subsidiary relationship that relates a company with its subsidiaries to the controls relationship in FIBO. It's important here to note that, actually, we have to, in order to be able to see through FIBO data that are defined with respect to other ontologies, we need to have the FIBO primitives always to be the more general ones in this kind of mapping. So in this case, we define that the class organization from DBpedia is subclass of formal organization, because we don't want to define them equivalent, because it's dangerous, and it's very rarely the case that two classes are truly equivalent. And we should always, in these kind of mappings, use For the upper level ontology, we should pick the more general class or the more general relationship. So enough about it. Yeah, you can see that, like, if you have a look at this diagram for the FIBO part, and if you, for instance, look at the autonomous agent in FIBO, it has like 2.5 million instances. And these are all the instances that we saw before. It's just that because of this mapping between the classes, we see them as instances of classes in the FIBO ontology. Good. We finally got to the part that has more to do with the demonstration. Part of the whole setup is what we call semantic press-clipping. So this fact that we have very good quality and fine-grained tags that relate entities and concepts with pieces of text that refer to them is very useful because, for instance, if you in a normal press-clipping exercise with the more mainstream technology, if there is Paris mentioned in the text, you never know whether that's Paris Hilton or Paris in France or Paris in Texas. While here we basically do this disambiguation and we reduce considerably the noise. The other important thing is that you can also trace and monitor, for instance, news not just about a concrete entity, but also like the other related entities like daughter companies and these kind of things. So the first example that I'll demonstrate is just to have a look in the news to see references to Volkswagen Group. Good. So we essentially say, well, there is an entity, and an entity variable, we bind it to Volkswagen, and then we say, well, let's get all the related entities that are related to this one that is currently set to Volkswagen through these controls relationships. So all the entities that are controlled by Volkswagen, union with Volkswagen itself. Then we get from the news mentions of such related entities, and in this case we put a filter of, like, let's see Volkswagen related entities in the news for April 2015, and you easily get this back. So you see there are plenty of news that actually some of them refer to Audi, others to Porsche, to MAN, to Lamborghini. Well, there are a few that refer to Volkswagen itself, but also Bentley, Skoda, Seat, and so on. So we have this information constantly streamed in. So we regularly getting this metadata from the now Semantic News demonstration service. So if I look into April, we will see some other news. And the latest one, being from the 27th of April, that's yesterday. Something about, well, poor Volkswagen. They're again about these scandals with emissions. Anyway, if in this webinar setting we had the chance to let you speak and get recommendations, I could have played with anything, because that's life, and it really has can retrieve all sorts of information about entities that are, say, in one of these data sets, like the Wikipedia. If we try this thing with Gazprom, you see that Gazprom is way less popular than Volkswagen. So in April alone, there aren't many news, so I can play with it. Say, let's see, March and April, and then we get 12, and you see that, well, it's about the football group Zenit in St. Petersburg that's controlled by Gazprom and a few others. Okay, that's probably enough about it, because that's, again, a relatively basic thing that you can do in this setup. We spent probably about a day to refine the industry classification that's already available in DBpedia. At first look, it looks very messy, but yeah, really within several hours to one day of work, we managed to structure it and clean it up to the extent to which it provides, at least to our impression, very relevant information. So this way we can see that, for instance, the out of the top level industry branches, that the most, let's say, populated one is finance, with 5,056 organizations that are within this industry sector, then transport and so on. You can do it in a more fine-grained manner also. Let's move ahead. So you can make all sorts of queries about the most popular companies or organizations in each industry. And you see that, like, you get General Motors and Tesla and Volkswagen on the top. But in this case, these are references that are just to the entities themselves, without the related entities. So if I make it again for this way, we can see again ranking by news popularity of the entities in the automobile industry. That looks different this way because we already now include references also to related entities. And yeah, you can do it for any industry, like and yeah, out of a sudden, Walt Disney and Fox are on the top. So the way in which we calculate this is that we say, well, we are searching for, it looks probably complex, but it's not. So we say, well, industry is said to be entertainment, and then let's get variants of entertainment by using this predicate. And then we are searching for a parent organization that is denoted to be part of one of the variants of entertainment. And we have this very well structured in the database. That was part of the cleaning exercise. So we want this parent to be a company. And what's more important, we don't want this parent to have on its own a parent that is in the same industry. So out of a group of companies, we want to work with the top of the hierarchy. And then for those, we get entities that have this parent as a parent is a transitive relationship, and so on and so forth. So let's consider it groundwork. You can see how results like differ, and how if you make it just measuring the popularity of a concrete thing without the related entities, the ranking of the automotive companies looks like what you see on the left. General Motors on the top, then Tesla, Volkswagen, and so on. And if you include also mentions of companies controlled by these guys, then the number for General Motors almost doubles, and the number for Volkswagen doubles, and Tesla goes number 4. For the France of BMW gets some. Yeah, if you consider related companies, it gets in top 10. If you don't, it doesn't. Good. You can do this for all sorts of industries. Like if you do it just for, you can either do it for finance, that's the more general category, and includes also investment funds and stock exchanges, or for banks. And here you see that without controlled companies, Goldman Sachs is first and JP Morgan is second. And if you include controlled companies, well, what we have here, the top seems like a noise. You will have the time to look at it and see what's in and to clean it up. But then underneath, you see JP Morgan Chase like getting it together with the children. You almost double the figure. So without children, you have 856 references to JP Morgan. With children, it's like almost 2,000, and it gets above Goldman Sachs. So being able to do this and basically do even press-clipping or ranking or trend analysis on this basis, including related entities, makes massive difference as compared to the plain one when you don't. You can also do like things like measuring the regional popularity or exposition of a company. So with this type of query, we say, let's see how often Toyota and its related entities are mentioned in news that are mentioned a specific country, or that are somehow related to a specific country. And if you run this, you get like, well, United States being by far leader. The reason is that in this news stream that we are currently playing with, US is overrepresented. So it's I mean, this gives natural bias to this kind of statistics. So one can, to avoid this, we did a bit of normalization, and we now do the same calculation, but we also get country score that we use to basically normalize the flat count that we're getting out of just counting the reference in the news. So that's normalization that takes into account that one country is overrepresented compared to another. Well, in this case, that's for British Petroleum. Let's do it for Toyota first. So you see that we see something that makes slightly better sense. Like Japan jumps up at the top, and Mexico and Spain appear because I believe they have facilities there and this kind of stuff. And then you can do this for anything you want. I played before with British Petroleum, and here you see that this normalized exposure towards concrete countries is bigger for countries like Angola, Mexico, Norway, Ukraine. These are countries that either have oil and gas, either have like pipelines like Ukraine. So that's again an interesting tool of assessing the level of exposition of a concrete organization together with all the entities that are related to this organization, like subsidiaries and so on and so forth, to specific geographic regions, and then use it for further analytics. Good. So now let's get to what we actually advertised to this call. Discovering suspicious relationships between companies. Let's start over with control-related chains that go across different countries. I have already pasted this into just a second. In my browser to save time. So here is suppose that you have company C1 that controls company C2, and C2 controls C3. Then for each of these three, you get the countries where these companies are based. And then you say, well, to make sure that it's a cross-country relationship, let's make sure that C1 and C2 are different. So the easiest thing to do would be to see first the relationships that come up. So I will simplify the query. And you see, for instance, that the Qatar Investment Authority controls Volkswagen, that controls Audi, and the first is in Qatar, and the second is in Germany, and the third one is in Germany. And then Warner Bros. Controls EMI, that controls Capital Records, first of which is in the United States, and the other two are in UK, and so on and so forth. So what the original query was about was to see what combinations of countries are most popular for this type of relationships. So we see that there are 451 representatives of the pattern where a company from United States, oops, I changed the sorting of the results. So a company from the United States controls company in Canada, that controls another company in Canada. That's by far the most popular pattern. And then the second one is the same, but the company in the US controls another company in the UK that controls another company in the UK, and so on and so forth. So next, the target is to control other companies. So to look for patterns where one company controls another company when these two are in the same country, through a company that's in the middle of the control chain that is in a different country. So this query looks like this. So we have C1 controls C2, C2 controls C3, then C1, we get the countries, but notice that we want C3 to be based in country C1, so that the binding of these two variables in these two triple patterns should be the same. So we say C1 and C3 should be in one and the same country, and C2 should be different from C1, C2 country from C1 country. So the one in the middle should be based in a different country. And when we do the same thing, we see again the most represented patterns. The most represented patterns are that a company in the United States controls another company in the United States through a company in the UK, and then vice versa. So these two economies seem to be fairly well interconnected. And then the same between Italy and United Kingdom, France and Japan, and so on and so forth. Now let's make it even one step more interesting and say the one in the middle, this company that is in the middle of the control chain, it should be registered in an offshore zone. And that's what we do with this query. So it's the same stuff as before. We only say that C2 country should have offshore provisions. Because, you know, there are plenty of countries like the Netherlands, which aren't, they're on the mainland, they're very well developed economies, but they still have in their legislation provisions that allow offshore type of registrations. So if you do this one, we see that, for instance, Big Food Entertainment controls Fashion 4K through Fashion 1, and the first and the third Big Food Entertainment and Fashion 4K are registered in the United States, but the one in the middle, Fashion 1, is registered in Hong Kong. Then, yeah, another pattern that you easily see here is that Bertelsmann controls many of the TV channels like RTL2 and others through RTL Group that happens to be registered in Luxembourg. So this probably has something to do with the tax optimization opportunities that the Luxembourg legislation allows. What else? Yeah, we see, for instance, Essar Group that controls Essar Oil, and these are both in India through a company, Essar Energy, that's registered in Mauritius. I don't know how many of you have been to Mauritius, but it's a good place, so they probably decided to register the company there to make sure that the board members have better entertainment opportunities. So we're getting this type of information extracted. I am personally disappointed at this phase of the experiment that we have only 25 of those represented in this data set. This has something to do with a few things. Point one, we still haven't mapped all the GLEI data, GLEI entities to DBpedia to be able to get benefit of the synergies between the two data sets. When we do this, we expect to see more. The other thing is that on DBpedia, people usually don't publish offshore companies. They actually publish the companies that are the most popular ones, and the offshore middlemen are precisely the opposite. And we also haven't included in this analysis the information about company relationships from news, because we're still working with this one. So there are plenty of ways to make this better, and I hope that soon we'll be able to show you these kind of things. We started playing with analyzing the relationships that we extract from text. Like in this case, this table demonstrates relationships from text that are three types: affiliated organizations, relation acquisitions, and relation mergers. Merger relations. And we see that across these three categories, we have extracted 455 relationships of this type from news between Chrysler and Fiat Chrysler Automobile, the combined holding company, which is not strange at all. But in some other cases, it may be more interesting, and it will be more interesting. So we are just essentially beginning this kind of analysis. So what else we plan to do? As I said, we plan to do better mapping of these legal entity identifier data dumps from the corporate registries, company registries to the rest of the data. We'll make a bit more experiments with ultimate parent relationships. The most valuable of all for this kind of work is to be able to use commercial data sets like DBpedia, Bureau van Dijk, Factiva, FactSet, and others. We actually have access to such data, but we are not allowed to publish results based on such data, and we're working on this type of partnerships. So that's coming soon, and this will make a big difference, because if you remember from in DBpedia there are 500,000 companies, and the leading vendors of company databases have in the range of 200 million. It's relatively straightforward to do analysis for organizations that are related in the news, but are not related in the data set. So this allows us to essentially extract information. At least have a look at it and say, well, why these two things are so much related in the news? Is it the case that we have an omission in the database that should be completed? Solved, or it's something else, or it's something suspicious, whatever. Good. So at the end of the day, to make a perfect working place for someone like the risk analyst or the compliance manager that's trying to use this kind of information in his daily work, we will be essentially generating profiles of entities, presenting all sorts of information about them that we managed to retrieve this way, like suspicious relationships and exposition to different regions and popularity, timelines, this kind of stuff. So in a way, we'll enrich what you saw as a topic conceptual page that demonstrates related information about concrete things. Good. So to wrap it up, we show that it's easy to map open data to an upper level ontology like FIBO. We demonstrated that integrating yet another data source can happen with very low efforts, like with this GLEI data, legal entity identifier data. It took us literally a couple of days to get it archivized and then to get the first phase of matching and reconciliation that links information about the same entity from different sources. It's really great to see that you take two data sets and it can happen in days rather than months or years. There are all sorts of analytics that can be performed on metadata extracted from text, like what I demonstrated: popularity ranking, regional popularity, regional exposition, relationship extraction, of course. We built most of this stuff as a sandbox, but yeah, that's all based on products of Ontotext that are already used by some of the biggest media and publishers, like GLEI, the database engine that I was torturing in the course of this presentation. Open Policy deals with vocabulary-based searching, like legal documents or big documents of any type. And Dynamic Semantic Publishing platform is what Financial Times, the BBC, and others are actually using for their business. So thank you very much for your attention. We're close to the hour. You can play yourself with our semantic news portal at now.ontotext.com. Most of the technology pieces that you saw can be used out of Amazon. We have the S4 service, self-serving semantic suite, where you can easily start playing with the database engine or with text mining pipelines. They're quite reasonable, free quotas, so you can start playing without any installation overheads and payments and so on. And of course, you can always reach out to us. So that's what I had.
All right. Thank you very much, everybody, for tuning in. Please stay on while Athanasis Kirakov is reading the questions that you've submitted. I just want to let you know, guys, that, again, you're going to receive a recording of this webinar, so don't worry if you missed anything or you haven't taken notes. You're also going to receive the presentation and slide share. And I would like to remind you, we're also having upcoming webinars, which you can also subscribe. And I think that Naso is really liking this topic, so probably he'll do another one. I'm not trying to push him, but I think he actually really enjoyed this topic.
Yeah, actually, we plan to release this sandbox as a public demonstration platform, FactWatch News, sometime in May. So it's coming really soon, and then I'll demonstrate all these further analytics that we spoke about as future work.
So you can expect another amazing webinar with NASA probably in May when we release FactWatch, where he's going to explain more and more, I guess.
Okay, so let's see some of the questions. Stephen Krause is asking, have you loaded these into one location, GraphDB, or can you query the individual endpoints virtually? In this concrete case, we have loaded them as a single instance of the database, but we can also query those individually. This can be done with a feature of the query language called federation. In Sparkle, you have support for federation, so one can easily, for the part of the query, use data that's coming from a different Sparkle endpoint, a different database that can be hypothetically, geographically very distant. There are many cases in which we need to do so. But for analytics purposes, yeah, most of the time you don't want to do this because there is a serious performance penalty if you have to join information that's from two different servers. The other question is from Stefan. How exactly do you do the GLEI mapping? Well, I mean, that's a sort of a ETL problem or data integration problem, and in this case we experimented with using the Lucene connector, so using full text search to do this kind of mapping and counting on the relevance scores provided by Lucene if you configure it in the right way. So we have a connector that essentially allows us to get specific patterns out of the triple store to be fully indexed in Lucene, and in this case we basically indexed all the information about entities and their names and descriptions from Video. We have a Lucene index for this, and with with the appropriate query, you easily get candidates about, I mean, the most likely candidates. And then if you combine this scoring, simple scoring that comes out of Lucene with some constraints, like in order to map two things, I want them to be in the same country, this kind of stuff, then it works very well. I mean, it's a single Sparkle query, and yeah, the accuracy of this mapping is above 95%, above 98%. So, of course, one can do it in a more precise manner, but for our purposes, we use this basic mapping. Yeah, that's probably enough. I'll get the rest of the query, the rest of the questions answered over email. Thank you everyone for attending and listening.
Thank you very much, and enjoy your day, evening, or wherever you are in the world. Please have a good day.